So ask the question, what other recurrence relations have this little property? And one example that I like that was actually pointed out to you, the recurrence relation for the integers. I like to use it as an example. Take the sequence where you take 2 of the previous terms and subtract the term before that, starting with 0 and 1. So that the next term is 2 of these minus 1 of these. Right? That's 2. And 2 of these minus 1 of these is 3. And so on. And this is just basically the integers. Okay? And it turns out that this recurrence relation has the same deal. So for example, I did m is equal to 2 before, I'll do m is equal to 3. Say I start with some number, 2, and I take every third number, which is 5, 8, 11, 14. So this is a subsequence that I took every third number, 17, 20, right? That's how it goes. I took every third number, so I take the third root of these numbers. And I obtain this sequence here. Well, this sequence has that same behavior. It wants to go back to this original guy. That is to say that the cube root of 20 is approximately 2 of these minus 1 of these. 2 of the cube root of 17 minus the cube root of 4. Does everybody understand the behavior that we're observing here? So in general, we basically are saying that an minus 2, an minus 1 plus an minus 2 is 0. We represent it this way, showing that it's homogeneous. And we take the mth root, but we're taking every mth number. Right? an minus 2m to the 1 over. And we want to show that this goes to 0 as well. But we want to do it in a general setting. For any recurrence relation, find conditions for which we'll observe this property. So, so in general, a recurrence relation is a sum of, you have some coefficients here, and you have a linear combination of terms, basically. From 0 to let's say some number k. Homogeneous sublinear recurrence relation. And our question is, does the limit as n goes to infinity of this guy here does this equal 0? In other words, when we take every nth number and we take the nth roots, is the error going to go to 0? So it is it's this beast that we wanted to analyze. We take the same approach where we associate a polynomial where we just replace this by x to the, just like we did before, differential equations. You're solving Euler, what do they call those? Linear differential equations with constant coefficients. You take the characteristic polynomial, you find the roots, you express it in terms, depending on the multiplicity. Remember the multiplicity, you have solutions. Anyway, so we associate this polynomial here, x to the k minus n, which I can factor it in terms of its roots, say like this, from u going from 1 to s, and times with some multiplicity. Polynomials, factor them out into roots.
What happens if they're repeated roots, though? Isn't there something else?
Then, yeah, that's the multiplicity. It's raised to some multiplicity.
Oh, so you still, like, because with differential equations, you throw in an x.
Yeah, exactly. You throw in a polynomial of degree 1 less than your solution. So then the multiplicity of the root. So if you have multiplicity 3, your solutions are going to be e to the x times and then x squared. That's your general solution, and then some linear combination is just a polynomial is e to the something times a polynomial of degree in x of degree 2, because the multiplicity was 3. Right?
And nothing, you don't multiply by a correction factor when you do it for recurrence relations, or do you?
No. I don't know of any correction factors that we multiply by. No,
I don't know. That's the term I'm using making up right now, but I'll just.
Oh.
Yeah.
No, we don't.
Okay.
Yes, then the answer is clear. No, we do not use this correction factor that you talk about.
All right.
That you speak of. So the polynomial, I write it this way, and now I can represent my recurrence relation, an, in terms of these roots here. So it'll be, I'll take a root, say the qth root, and I'll raise it to the n, but I gotta multiply it now by a polynomial in degree of a polynomial in n of degree 1 less than n.
Oh, that's all right.
Okay? Are you guys, when we did
One less
the,
than n cubed.
what?
Polynomial of degree 1 less than n cubed.
A polynomial of degree 1 less than n cubed. So we can write it as a sum of, it's a polynomial in n, say j from 0 to m cubed minus 1. N to the j and some constant here that's going to be dependent on the initial conditions. This is the recurrence relation. And of course we got this specifically because we set these initial conditions. You set other initial conditions and you'll get some of the sequence. So that's what these guys are dependent on. They're dependent on whatever initial conditions you set. So if you have this, if you define yourself a recurrence relation, just how you're going to add it up, you still haven't decided what your initial conditions are going to be. But we don't care to go that far. We just want to know, just from this, what can we tell? So for each root, I raise it to the nth power and multiply it by a polynomial in n of degree 1 less than the multiplicity of whatever that root happened to be. And then I add up all of these guys here. So this will sum up from 1 to s. And this is basically a general solution. Where I guess maybe I need another index here.
So that in total you have as many coefficients as is the degree of the recurrence relation.
Exactly. I have.
And since you have
Yes,
roots,
because that's how many initial conditions will uniquely determine a sequence.
well, the general theory says that the solutions to this homogeneous thing is a vector space of dimension this. If you want to find the basis, you need to get exactly this number of basis elements.
That is not surprising. Absolutely. So then, what do we do from here? We want to investigate this guy. And a main problem that we're going to need is, or a quantity that we're going to need is this guy. The limit as n goes to infinity of 2 consecutive terms. So this might be a little rough to calculate right here. But I basically, this is an, and so what's an plus 1 going to be? It's going to have a plus 1 here and n plus 1 to the j. Okay? So let's start. I don't think that I'm going to be able to go through all the calculations right now. So I think I should probably start just getting to what the results were, as opposed to going through all the tedious work. But you can see that it took something, and in this case, it's going to be a little bit more. So just to give the result, this right here. Okay, before I say that, let me do one more thing. Suppose that I ordered these roots according to magnitude, so that the first guy is the biggest one. R1 is the biggest root, and then all the other ones gets smaller and smaller in terms of its magnitude. Okay, so that R1 is the largest root, the root of largest magnitude, and that this will converge to this, of course, if the magnitude of the first one is strictly bigger than the magnitude of the second, of the one that comes after, because you can have two roots that are the same magnitude. Say they're complex, two different roots, or even just +7, -7. Two roots that are at the same magnitude, but if the one with the largest magnitude is strictly bigger than the one that comes next, or perhaps maybe they are the same, but the multiplicity of the first one is bigger than the multiplicity of the second one, then you'll get that this converges to this largest root here. And it's really not hard to do. You just factor out, you write an plus 1 like this, you factor it out, you take the limit, and it's r to the 1. So that's that. Then the next thing we're going to need to do is suppose I did an to the L. It's just going to be r1 to the L. So if I take this, of course, is saying that when we have the Fibonacci numbers, you take the sequence of ratios for Fibonacci numbers of 2 consecutive terms, the ratio of 2 consecutive terms. Well, we know that it goes to 5, the golden mean, and that was the root of the largest root in the characteristic polynomial. So if you take two terms that are apart, then it'll convert. That ratio will converge to 5 squared, and so on. And in general, this recurrence relation, it's going to converge to the Lth power. If you take terms that are L apart and take that limit of that ratio, it's going to converge to the Lth power of the largest root. Okay. So that's that. And the next thing we're going to need to do is, I said a little something here about how, when we say that this thing is getting closer and closer to the number, that it's a good approximation, we mean that it literally is becoming the same number, that it's not somehow asymptotically they get to within, to kind of be a good approximation to each other, because the scale of the numbers you're talking about, the error between the numbers is so small compared to the scale of the numbers you're talking about, that relatively speaking, the error goes to 0. But indeed, the absolute error, like the absolute error goes to 0. The actual difference between the numbers is what goes to 0, not just the ratio of the numbers. So that was just something that I pointed out here. But basically, the result is that what I found was that if any one of these conditions is satisfied, so this will be quite a bit, but let me just write it. If the multiplicity of the multiplicity of 1 is 1, or if R1 is equal to 1 but greater than R2, and the multiplicity of 1 is equal to 2, which, by the way, I think is what happens for this recurrence relation here. You get this case here, and so this is why it works. Or if you have this being greater than 1 but equal to this, and both multiplicities are 1, or if you have this is equal to 1 and this is equal to 2, but the multiplicity of 1 is equal to 2 and the multiplicity of the second root is equal to 1. If your recurrence relation, you take the characteristic polynomial, you find the roots, you order them in terms of magnitude, and if they satisfy any one of these 4 conditions, then they'll have the property that we're talking about. Taking subsequences of m numbers and taking the nth roots, they will converge back to the original definition, which is here.